What? Are you talking to me?
I asked if the stream is HDR.
All right, let's get started. So today we're going to be doing a couple things. First, in terms of logistics, so I will be out the rest of the week. On Wednesday, you'll have a guest lecture by Marjana, my postdoc. So you'll also have a quiz that is centered around essentially giving her feedback on the lecture and any interesting things that you learned from it. So that will also be streamed live on YouTube. We just figured out how to add 2 people to this account, so remote people can watch it as well. Okay, regarding other stuff, your final projects are due May 17th. The report template has just been released. It is very similar to your proposal template, and you can reuse some of the sections as you see fit. So several of you have been coming to our office hours discussing like updates to your proposal plan. That's great, and we encourage that. Keep in mind that if your project does deviate considerably from what you proposed in the proposal, you will want to run it by whichever one of the instructors was assigned to your project. So yeah, I think there will be just this one more quiz, which is associated with Marjana's lecture. You have your homework, which is due in 10-ish, 12 days or so. And then you have the final project report. So those are your deliverables. A number of you have asked for the extra credit weighting. I'm still figuring that out, but I will post it on Piazza this week. So, okay, any admin related questions? Yeah. I'll talk about the midterm in this class. The last homework is being graded right now. It should be done. It's supposed to be done this weekend, so hopefully very soon. Other questions? Okay, so let's get to the midterm. So we finished grading your midterm, but the grades have not yet been published for reasons that I will discuss in this class. I do want to go over the solutions to the exam, at least roughly, just so you get an idea of, if you got a problem correct or not. But first, yeah, there's unfortunately a huge amount of cheating that happened on this exam. So like 25-ish students, when we were grading, we noticed that they had almost identical, also incoherent and wrong answers to almost all of the problems. So it is, yeah, very unfortunate. We're still trying to decide how to proceed with like this huge number of cheating cases. As you can see here, there was to be no collaboration on the exam. It's an exam. One thing that makes this a little hard is that all of the cheaters got grades that were far lower than the class average, so it really didn't help. It actually might have hurt and might have instead used, an AI or something. So some of the grades were so low that giving you a 0 on the exam is just like giving you 10 points off your exam, which is, not really fair to those of you who did the exam legitimately. So we are in the process of compiling all of the very obvious cases, of which there are so many, and we'll follow up with that subset of the class probably later today with options on how to proceed. But yeah, for the rest of you, the exam, it was hard. The average was about 50, which would make it the second hardest exam that I've written. And I think the fact that it was adversarial to GPT-4 inherently made it more difficult than I would have liked it to. It was very hard to write easy questions. I think in the future I have to go back to in-person exams, unfortunately. But a number of you did very well, which is great. So I'm going to go over the questions, and then yeah, you'll have an opportunity once the grades are published, hopefully either later today or tomorrow. You'll have a week to dispute any of the grading via regrade request on Piazza. And you can also come into our office hours to discuss with the person who graded your problem how whether it makes sense to have this request. But you have to submit your regrade requests by next Monday or Tuesday, depending on when we publish the grades. So that'll all be announced on Piazza. All right, so let's take a look at these questions. They actually were kind of ordered, turned out roughly from easiest to hardest. The first two problems most people generally did well on. So this problem was about a kind of issue that's happening during the decoding algorithm process, where this person, Lorelei, is trying to run GPT-4, but in a highly quantized setting. So this means that she's taken all the parameters of the model, right? These are, real valued floating point numbers. She's essentially compressed them each to be one of 16 different values. So this obviously saves a lot of storage, but it's also causing this issue of when she samples from her model using nucleus sampling, regardless of what she sets this p-value to, she observes different samples from the model. So we first ask you which value of p in the nucleus sampling algorithm, like if you set the hyperparameter to a particular value, which value is this behavior bizarre for? And so the value that it's bizarre for is 0. So at p equals 0, nucleus sampling is equivalent to greedy decoding, and you should get the same output every time you sample. However, a number of you said this is bizarre for very low values of p, which we also gave full credit for. So if you have a normal model and you're using nucleus sampling with very low values of p, you should observe almost deterministic behavior, but here she's not. So then the next part of this question asks her, why is this happening in this quantized model where everything is 16, every parameter is one of 16 values, and why is it not happening in the normal model? So if you think about it, and also if you read about it, or even ask GPT-4 or whatever you were doing about this problem, you will note that quantization has some issues. One of which is that it introduces a lot of ties into the final probability distribution. So you're squeezing all of these values together into 16 different bins, essentially. And so at the output layer, you might have a very, very small difference between, say, students and undergraduates or something like that, which now could result in an identical probability. So the hint that we gave you here, like this code snippet, it was intended to make you look at the documentation of the nucleus sampling function in PyTorch, where you would find that in the case of ties, this sorting algorithm that it uses is not stable. So it will just pick an arbitrary one of the tied words to output. So that's why you see this behavior in the quantized model. Essentially, if you said anything like it's due to ties in the probability distribution, you got credit. So essentially just testing your understanding of nucleus sampling in this problem. Yep. it says, while this is expected behavior for some values of p, which is like any non-zero values of p, it is not expected behavior for all values of p, which implies that she's trying all possible values of p, but for one of those, it's not matching with or for some of those, it's not matching with what she expects to happen. So that was the interpretation of the question.
Doesn't this mean that it's not matching for any value of p, for all values of p, she's taking this problem?
So basically it's saying that the behavior here is that she's obtaining different samples every time she samples from the model. This first clause says this is expected behavior for some values of p, right? So for any non-zero value of p, you would expect to observe this. However, it's not expected behavior for all values of p, meaning for all values of p, you don't expect to get different samples every time. Okay, sure. Yeah.
Just to touch on that 1.1, what I remember reading the documentation was sampling, the value p you set supposed to be, so when you use the sampling, you set that p to be 0.5, just accepting all of the values that are 0.5. So in this case, would p be some false?
What's that?
So
Are you talking about when p is 0?
yeah, so I'm saying when I read the documentation, you can sample, right? It says that the sample basically, when you said like p being like x, like 1 right? It samples everything, like all the logic that
That sum up to 0.3,
right. So
yeah.
would p here be from some let's say like instead of p?
Oh, so what happens if p equals 0 is, yeah, this is an implementation detail, but they always add the top most probable word. So it's basically if all values of p that exceed that, but you always have to have one value that you sample. So that is the reason why we accepted anyone who said very small values of p as well, in case you're not familiar with that. All right, let's move on. So question 2 was also quite interesting. So this was actually more of a tokenization problem rather than what some of you thought it was. So here there's a classifier that tells you with like 100% accuracy if something was in the training data of GPT-4 or not. And this classifier is perfectly accurate. It is an oracle. It obviously is not realistic to have this, but in this case, it is. So all of the details of the classifier are irrelevant here. It is just perfectly accurate. So the point is that the employee is saying that, like, you're not supposed to assume that the employee is lying. It says here, a lot of you did anyway, which, you know, it's okay. You got some partial credit for So the point is that this password is a sequence of 16 randomly selected English words. The key description here was that the classifier is trained on sentence level data, right? So it can tell you whether a single sentence is in the training data or not. It's not really clear that, first of all, these 16 randomly selected English words would be in one sentence, whether or not they would occur in a sentence along with arbitrary other words. So essentially, the whole problem was related to the tokenization of this classifier. So the reason why he cannot predict with certainty that his password is this string of 16 words occurs somewhere in the training data is because you could have arbitrary combinations of other words along with this 16-word password tokenized as a single sentence, and you would never be able to produce that combination to the classifier. So really just a problem with tokenization and how this classifier is set up. So a lot of you got this correct. This one, though, was a big challenge. I think we will give significant partial credit on this problem because it was quite tricky, and maybe the wording wasn't super clear. So here, the observation that Bruno has is that a lot of sentences that contain current events knowledge, which GPT-4 couldn't have because its pre-training data cutoff was September 2021, were being detected as in the training data. So the hint here, which some of you were able to understand, was that this pre-training data does consist of articles written before September 2021. But remember, models like GPT-4 don't just do pre-training, right? They also have many other stages of training, like instruction tuning, and of course RLHF. And we know, for instance, with ChatGPT, that happens on user queries that are issued well after September 2021, obviously. So the intent of this question was that the knowledge of things that happen in the future is coming from the human feedback data or the instruction tuning data, not from the pre-training data. However, a lot of you said, well, maybe some people on the internet wrote sentences that predict these events, and they were judged as similar, which, while not the intent of the problem, could be true for some subset of sentences. However, that wasn't really the intent of the question. So anyway, we will, I think now that we've finished grading, go back and be a little more permissive on this question in particular, because most of you did not catch on to the human feedback part of this problem. Yeah. Yeah, so let's say the password sequence is, for example, I don't know, place the microphone. That's the, let's say it's a 3-word sequence, right? And let's assume just that this doesn't appear normally, like it's not grammatical. You would never expect this to appear in a normal, news article or internet post. So if you put in the phrase place the microphone to this classifier, and it returned no, that this doesn't exist in the training data, that does not guarantee that this phrase did not occur as part of some other sentence, right? Because this classifier only tells you at the sentence level, does this occur or not? So if, for example, I had a sentence like, what is this person's name? Bruno's password is : place the microphone. You wouldn't, there's so many possible sentences that could include this password that you can't enumerate them all. So that's the point of the, yeah.
Technically, when you have large model they're trained on the internet, isn't there a chance that a random arbitrary sequence of 16 words?
Sure. So some of you did say that, and I mean that was this should work with any sequence of 16 words, right? So if you said that, that only might work for some subset of all possible 16-word passwords, but there was some partial credit assigned to that. In general, I do like to do this after we have published the grade, so you actually know what you said. But yeah, again, due to the, we still got to figure out the what to do with the people who cheated. For question 2. So it's unclear what retrieval mechanism is. So there is no retrieval from external data that is used by ChatGPT or GPT-4. That can be enabled with plugins, or for example, Bard has integrated access to Google search results. But in general, this model by itself is just all knowledge it has is in its own parameters. Yeah. All right. So here's where things started to get pretty hard. This question was trying to test your idea of your understanding of self-attention. And the first question, I'm not going to read through everything, but essentially the point of this question was that what if you just take a very long example that cannot fit in your transformer's context, and you chop it up into smaller sequences and then present these smaller sequences to the model in the form of a batch. So instead of having the child looked outside, saw it was raining, and cried, I could have these 4 smaller sequences instead. And now, maybe I can cleverly modify my attention such that I can attend over all of the previous examples in the batch and still have this context of 12 tokens while maintaining a sequence length of 3 tokens. So the first question most of you got correct. This approach that she described with just modifying the attention mask into this matrix doesn't actually do anything to the complexity of the computation, right? You're still attending over 12 things. Your model is not going to have enough memory to do this computation. So it was just like a cosmetic change that you made. It had no actual effect on the complexity of the model. So a lot of you said things like the common error for this problem was that people somehow thought that there should be this independence assumption between examples in a batch. That is not necessarily true. In fact, many machine learning models do not assume this. They actually compute stats over the entire batch and use it for different things. And there have been approaches that are proposed to specifically do this, like split a longer sequence into smaller chunks and then do some sort of retrieval over examples in the batch. So there's nothing wrong with doing things across different examples in the batch. It's just that this approach doesn't actually gain you anything. We also gave almost full credit for those of you who mentioned that the position embeddings need to be modified in order to support this modification, because if you imagine here, if you're at the word cried and you want to do attention over the batch, you probably want to know that raining occurred after outside, even though these are in 2 different sequences. So you might want to modify your position embeddings to kind of be 1, 2, 3, 4, 5, 6, 7, 8, 9, or something like that. But the bigger issue here is that this approach doesn't work at all. Yeah. All right, and then this problem was quite interesting. It's actually a very straightforward problem, but I think it looked very intimidating. So a lot of you probably saved this one till the end. This was showing you an example of kind of a fixed version of the setup in the previous case, where you actually are reducing the complexity of the model because you're attending over these compressed hidden states of previous examples rather than the actual tokens of the hidden examples. So the question here was essentially asking you for an attention matrix, a mask matrix, and like what would it look like, and also how would you shift the decoder targets. Okay, everything's working on here. So we accepted actually quite a range of solutions for the mask matrix. In general, if you said that all tokens in a particular example should attend over the previous tokens, just like in normal self-attention, and also over the hidden state that is given to you here, that was generally acceptable. Some of you did correctly modify the mask for this yellow part to kind of be more like the prefix LM. There's no reason why this hidden state shouldn't attend over this one, right? You can get more context that way. But we did not penalize you if you didn't say that. The decoder targets were more tricky for most of you. So the decoder targets are referring to what the model is predicting at every time step, right? And so in general, at W1, I'm going to be predicting W2. So W2 is my decoder target. But what are we going to do with these yellow tokens here, right? Like, it doesn't really make sense to predict any words from this cell, right? From this hidden state. What should I predict the next hidden state? It's not clear how to predict that with softmax layers. So essentially, we were looking for something that said you would shift the targets over such that only these words were predicting the next word. Some of you also said, you know, the last hidden state here could predict the start of the next sequence, which was fine as well. And one other thing we were looking for is what you would do with the loss function on these cells here. So you could mask out the loss function. You could just slice this so that you only compute the loss on these tokens. But you had to say something about that. You couldn't just say, we'll predict null here or something like that, because that, you know, that's not a complete implementation of this. So overall, the problem itself was not too bad. For those of you who attempted an answer, you were generally pretty close to correct. Yeah. Okay, so this question was about evaluation, and it had a number of constraints which made it quite tricky. So here, basically, you were asked to evaluate the summarization of an extremely long book. So if you think about it, if you wanted to do this, it's just not really feasible to ask someone to read the entire book and then evaluate your summary, right? You would have to, that might take days, and you would have to pay accordingly. So we were trying to get you to think about a way in which you could use humans to evaluate in a highly constrained setting where their cognitive load is dramatically lowered per example. So in particular, they were not allowed to read more than 1,000 words from each book. And so you can imagine the books are hundreds of thousands of words long, so this is you know, less than 1% of the book. You can only hire one annotator per book, so you couldn't just hire, you know, like 100 annotators to cover the entire book and somehow merge their decisions, although that would also have been quite interesting. That's not really clear how to do that. And they had to have some scale, so this part was just to get you thinking about how you would formulate your guidelines and how you would tell them what a 1 means and what a 5 means and things like that. So the first part here was kind of like a hint to get you thinking about how you might use a model to cut down the number of words from the book that the annotator would read. So this model here, a small pre-trained encoder only model, we were hoping that you would think of something like BERT. Many of you thought of other pre-trained models that you could find on Hugging Face that were like BERT, but then fine-tuned for QA or something like that, which was not at all intended, but I understand that is perfectly acceptable from this writing here, so we gave you full credit if everything else was also good. So the general way in which you might solve this with this model is to take chunks or maybe sentences from the summary, encode them using your encoder model like the CLS token, and also have the encoder model encode different chunks of the source books in whatever granularity you want, maybe sentences, maybe 100 token windows or whatever. So this was more related to the retrieval augmented language models that we discussed. Once you have an encoding of the summary sentence and an encoding of all these chunks in the book, you can then find chunks of the book that are most similar semantically to the summary sentence and essentially draw these alignments between sentences in the summary and chunks of the book. And then you can have the annotators read those chunks from the book to get some context in which to evaluate the summary. So That's probably the best you can do given these constraints, and it's certainly not a great evaluation, right? Because the annotators are missing a lot of context from the entire book, so they're never going to be able to do a perfect job. But given these constraints, doing this is likely better than anything else that you could do. So a lot of you actually got the general idea of this correct, which was nice to see. But some of you did not specify the guidelines for the annotators or how they might calibrate their scores, what process you would use to ensure high quality results. So we took off some points for that. This question was super hard. Granted, it is a hard question to begin with. I don't think anyone has worked on this before. But you have this like insanely long narrative, and it's also nonlinear. So if you tell GPT-4 to summarize a nonlinear narrative, it might summarize things chronologically, but then it just won't make sense when you read it. Like, it'll be incoherent. So we were trying to evaluate how coherent the resulting summaries were. So coherence, if you looked it up or asked GPT-4 or whatever, refers to how logically well connected the sentences in the summary are. Like, does it make sense when you read it? Or are things just coming out of nowhere and make no sense at all? So we were asking you to measure the coherence of the summaries with these highly nonlinear narratives. So there are many reasonable solutions. The best one that we found was to just toss the book away completely. So there's no need for the annotators to look at the book. Instead, they can just read the summary and identify somehow, like whatever, many of you chose different ways of marking the coherence. It could be identifying adjacent sentences that don't make sense together, identifying cases where it's unclear who is acting in this sentence or what time period it's located in or anything like that. But in general, you don't actually need the source book in order to evaluate the coherence of the summary. Obviously, it would be helpful, but in general, you're just looking at whether two sentences fit together or whether all the sentences in the summary fit together. So yeah, for those of you who propose some sort of method to measure coherence with or without the book, you got credit for this question. All right, any questions? Okay, and then finally, this one was, I think, probably the one where, other than 3.2, many of you got to at the end and maybe didn't have enough time to write out your answer. Here, you were actually asked to basically skim this paper on self-refinement to understand the method that's going on here, where a language model generates an output, then it generates feedback on its own output, and then it conditions itself on the original input, its initial output, the feedback that it generated about its own output to produce a better version of that output. And then that process can repeat as it does in this paper. So, and note that this is quite interesting that this even works, because the model is not changing, right? It's not updating itself, but yet it can somehow learn to produce outputs that humans think are qualitatively better than the ones before refinement. So if you read this paper, you will see things like, humans also follow this process where they might write a first draft and then they can find things that are wrong with it and fix them and improve their writing gradually. So these kinds of methods are inspired by that, and it's kind of amazing that this actually works with large language models. So here, the question describes that the variance of this method is really high. So sometimes the model generates some feedback and it's able to condition on the feedback to significantly improve the quality of the output. But other times the model generates feedback and then might actually introduce new errors that weren't present initially. So you had some constraints here, and you were asked to basically come up with a method that could decrease the variance. And the key here was step 3. So you're not allowed to generate multiple outputs in step 1, but we didn't say anything about generating multiple instances of feedback, right? And so I think most of you who actually answered this question caught on to the fact that if we can generate multiple pieces of feedback, then we can feed all of the different forms of feedback into the model and re-rank them based on which feedback was the best. Or we can do some re-ranking on the multiple feedbacks that we get and pick the one that is that the model thinks is best. And note that you can do this re-ranking using GPT-4 itself without any external data. You can ask it like which is the most coherent feedback or something like that. So we accepted a wide range of answers that basically involved generating multiple pieces of feedback and using that to improve the final output. So I think the biggest misconception here was, it wasn't too big. I think maybe 10% of you thought that we actually could fine-tune GPT-4, which you know, it clearly says you can't, but I don't know, maybe there was some misunderstanding somehow. All right, so that is the exam. Any final questions?
I'm curious to know what you guys did to obfuscate the exam for language models.
Oh, that's a great question. So yeah, as I mentioned, I wrote this exam to be adversarial to ChatGPT and GPT-4 specifically. I didn't actually, I think the TAs might have tried BARD and some other models, but those are significantly worse anyway, so I figured it wouldn't help. Essentially, I wrote a large number of problems, and I have this like graveyard of problems where one of these models solved it perfectly with just simply putting the question into the model as a prompt and with no other, I mean, you could give it an instruction like you are an expert in NLP and great at solving exams, and but it would, and this is especially true with easier problems, which it could just copy the answer from somewhere. One thing that I did find that was very useful is when you give the model multiple constraints on the answer, it does struggle a lot to understand those constraints. So that's why you saw things here where you know, it's like your solution must adhere to these constraints. That really proved to be tricky for the language models. That also might be something you could think about for the homework, which asks you to you know, fool these models. But yeah, there's nothing too fancy. Like if you were hoping we use some actual machine learning technique to do this, I don't think there is one that exists. But it's actually very difficult to do this. So I think that's another reason. I thought it would be actually straightforward when I started writing this exam, and I was very impressed. So yeah, in-person exams seem to be back on the menu. Yeah.
So did you guys experiment with like continuing the prompting after it got it wrong on it? Because like when I was doing the exam, I was using ChatGPT to help me.
Yeah.
And I noticed that when I would just ask it the question, like it would just completely screw up, like get everything
Yeah.
wrong. But if you like after it got it wrong, like explain like what you did wrong, like it was able to like make a more coherent answer.
Yeah, so we did not, but we thought that that would be a good way for people to use it to evaluate their own answers. Or, you know, in this method itself could be used for the exam. I didn't see anyone who reported using it like that, but a lot of people did use it like you just mentioned, where they wrote their own answer and then put it into the model and asked for feedback, and that seemed to be helpful. So yeah, that is perfectly valid. Yeah, we didn't experiment with that, but we thought that people would. Yeah. No, I think for some of these it got it wrong on the first try. But like once I figured out that it was bad at constraints, I just you know. And also note that this problem actually has a figure, so that was probably pretty hard for people to try and describe this in a, I guess you could take LaTeX code that generates this table. I'm not sure if people actually did that, but it wouldn't have helped in any case. Yeah?
Is there any correlation between like the amount of people who use the ChatGPT LLM and how they develop test?
We haven't yet done that analysis. We would like to do it, but that would involve, yeah, actually reading all the AI disclosures, which at this point we're kind of burned out from grading the actual questions. All right, any other final questions? Will some metrics be released on how everyone did? Yes, I will release this again once we address the cheating issue, but the average was around a 50 on the exam with a variance of like 13. The max score I think was like an 89. Several people did very well. And guess on how it will be curved. So the exam itself is not curved, but the overall grades are curved to, that details of that will be released closer to when we actually submit the grades. But yeah, the overall grades are curved, so it's not really on a fixed grading scale. Yeah. Any? I'll have to look and see, but it usually depends on the average of the exam and the final projects. I'll post on Piazza. Okay, so now we have about 30 minutes to get to the topic of today's lecture, which is understanding in-context learning. Sorry, this is really annoying. This. Okay, so just as a reminder, when we're discussing in-context learning, we are referring to this phenomenon where a large language model can solve a new task that sometimes it's never seen before, and it maybe could never have seen this task before in its training data, just by simply giving it some demonstrations of the task in its prefix. Right, so there's no training going on in context learning. You're literally just showing it examples of the task that you want to solve, and those demonstrations are influencing the conditional probability of the next word that the model is predicting. So here's an example from a recent blog post from Stanford. You can see here this sentence, or this thing on the left is for sentiment analysis. So we have a couple sentences along with some sentiment labels. We just put this into the prefix, put a test sentence into the prefix, and generate the label. The language model will predict positive or negative. And it's not that, in this case, we have no instructions, right? We just are giving it demonstrations, and it's somehow learning what the task is just from this. But we're not doing any gradient descent or any updates. So how is this possible? So when GPT-3 first came out and this behavior of in-context learning was first described and evaluated, many people were skeptical. They thought that, all of these new tasks that the model can solve, they've got to be just in the training data somewhere. The model has already essentially trained on them by predicting the next word. And so, it's impossible for us to know what exactly is in these trillions of words that are on the internet, right? There could be, so many different tasks that you might not expect them to be present in the data set, but they are in some version. And so, a lot of people thought that the model was just kind of doing really powerful pattern matching on the data that it's been trained on. This is probably, this is certainly happening to some degree, where a model is good at tasks that it's seen before in its pre-training data, right? it makes sense that it would be good on these things. But a lot of people in kind of objection to this hypothesis also proposed new, increasingly more complex and weird synthetic tasks that these models could learn anyway, despite having, you know, a very, very tiny chance that they occurred in that form in the training data. And so one question is like, what mechanism do these language models have to solve these tasks with absolutely no training and no ability to see those tasks in their pre-training data? How could this even be possible? And so, you know, when GPT-3 came out, there was no answer to this question. People generally resorted to, well, it's just memorizing its training data. You know, and a lot of people thought that because of the frequency of lists on the internet, right? You have things like, here are all of the tallest buildings in the world, and some sort of list like that. You had kind of formatting where you have a sentence in one language and another sentence in a different language on the next line. So maybe all of these kinds of things really helped the model kind of generalize, at least in terms of the format, to new tasks. However, more recently, just in the past year, there's been a lot of work coming out that shows that, you know, although these kinds of language models do memorize a lot from their training data, they are also capable of kind of simulating smaller models in their parameters and training those smaller models. And they do all of this just with the self-attention and feed-forward operations without actually updating their own parameters. So all of the learning is happening in the activations of these models, which sounds very bizarre, right? What does that even mean, that a language model has a smaller model that it is training by itself? So we'll get to that towards the end. But first, I wanted to highlight some aspects of demonstrations that we haven't talked about. So in this example here, I give you something like paying off the national debt will be extremely painful, and this is associated with negative sentiment. All right? And you might think that the most important aspect of this demonstration is that it shows you an instance of a sentence that has negative sentiment along with the label that the model is supposed to predict. So there's this mapping between the input and the output that is highly relevant for the model to learn this task. So this paper by Sewon Min in NLP 2022, so just in November, showed that that's probably not the only reason why a demonstration is useful. In fact, they show 4 different aspects of demonstrations that could be helpful in helping the model to generalize to solve the task. So one is the distribution of inputs. So this doesn't consider the label space at all. Here it looks like we have sentences from these kinds of, business articles or something like that. So maybe the distribution of the inputs that you show in the demonstrations already tells the model, okay, you should expect sentences that have something to do with this domain. Then the label space itself. So irrespective of the mapping between an input and a label, it could be interesting to know what are all the possible labels, right? So here you see 3 different labels. So that might clearly tell the model that you should predict one of these 3 labels and not anything else. And of course, the model can also decide to predict a new label whenever it wants, but showing it these the unique labels in the demonstrations at least gives it some soft constraints on what it should produce. We have the format, right? So what is the format of the input and the output? Here you see the sentence followed by a new line followed by the label. In this case, you see the sentence followed by these slashes followed by the label, right? So this tells the model how it should generate the actual output of the task that you care about. And finally, there's a thing that we discussed at the beginning, the mapping between the input and the label. So knowing that this is a negative polarity sentence. So there's these 4 things, and it's not really clear which of these is most important to helping the model solve a held out example. So in this paper, they did several very interesting experiments on classification tasks, just classification kind of tasks. So here, there are some plots showing what happens when you have demonstrations with the gold label, so that's this orange curve here, and demonstrations with a completely random label. So you could just shuffle these labels. Obviously, that destroys the input to label mapping, but it preserves the other 3 aspects of the demonstration. So what is the impact of that? And you see this with varying numbers of demonstrations, so that's the K here. And you see that it barely makes a difference, right? So if I say paying off the national debt will be extremely painful, if I say that that's positive, that doesn't really fool the model into thinking, oh, I should not predict the sentiment of this sentence. It still generally understands the task that you wanted to solve, even with the wrong labels in the demonstrations. So that's pretty surprising, number 1, that the actual semantic connection between the label and the input doesn't seem to affect the model's performance. So what about other aspects of the demonstration? So the paper also manipulates each of these 4 different aspects. So you see here the demonstration along with the gold label. That's how this looks. And it preserves all 4 of the aspects. Then what we just saw, demonstrations with random labels. So here, this one is a neutral sentence now. This is a negative sentence. Now, they do even more perturbation. So what if instead of having these in distribution inputs, you have random sentences selected from the internet as your input, and you pair them with random labels. So here you see color printed lithograph, very good condition. Like obviously this is not really a sentence that, actually I guess very good condition has some sentiment here, but in general, like you wouldn't expect any random sentence to contain sentiment, right? But you're still giving it the distribution of the correct labels, right? So this is even though they're not meaningful. Here you see the impact of modifying the actual labels themselves. So instead of producing neutral or negative, the demonstrations are random words like unanimity and wave. So here the model doesn't even know that it's supposed to do sentiment, right? It's just getting these random words that it's supposed to be predicting. And then you can just remove the labels completely. So here you just have random sentences that might contain some sentiment or might not contain some sentiment. And then you could just do the labels only. So you just give it positive and neutral and negative without any inputs. So there's all these different configurations of the demonstrations themselves. And the paper examines what is the impact of these modifications on the performance of the model on these tasks. And they experiment with a bunch of different models and essentially decoding strategies with all of these configurations. So first of all, you see that so let's just take a look at GPT-J, which is like an open source version of GPT, some decoder-only language model. You can see that with known demonstrations, the performance is pretty bad. With gold labels, somehow the performance with random labels is even better, which is surprising. The worst one here is random labels only, which refers to, I guess, these random words here. I guess that makes sense. It'll have no idea what the task even is. But you can see that these different properties make a big impact, and most of them make a bigger impact than the difference between the first 2 bars here, which is gold labels versus randomly shuffled labels that are still in distribution. So overall, these plots are showing that the mapping between inputs and labels may not be as important as all of these other aspects, like the format, the distribution of the labels, the distribution of the inputs. Does that make sense? Yeah. That's a great question. It's a big limitation of this work, as I'll get to in a bit. It's not really clear how you would attempt something like this with a more complicated task, just because the evaluation for those tasks is not as easy. Here you can just look at accuracy or F1 or whatever, but with other tasks it becomes more complicated. Would be interesting to try in, for example, like machine translation. Other questions? Yeah, no, go ahead.
In the format, they completely remove the output label, but the format should also feel like, for example, you have that arrow pointing
Yeah.
in the question to the answer. So not having that consistent messing it up in the
Oh, I see. Like using different formatting? Yeah, I don't think they tried that. I'm sure that would hurt the performance as well. Other questions? Okay.
Thanks for the nature of that. I think that the record label only refers to the adopted version where the sound becomes the label language.
Oh, I see. Yeah, possibly. Yeah, because it has the the input distribution and the format have been removed, but the label space is still preserved. Yeah. Yeah, this one. Yeah. Yeah, so that also is not ideal, right? Because if you have this input, the next word is very unlikely to be like positive, right? It might just be a continuation of this sentence. So, but that is part of what they're evaluating, right? In all of these cases, you just take the next word and evaluate it as correct or not. So the model could generate any arbitrary word. But yeah, it's a good question. Yeah, that's a good question. So in, say, ChatGPT, when you're interacting with the model, you may only need to give the demonstration in the first prompt, and then you can give it like iteratively more and more test examples. But that's because the first prompt still stays in the context of the model, right? It essentially will just concatenate all of the different turns in the conversation together. Yeah, most of these experiments are not done with chat-like models. They're all done in one input prefix. Yeah, so I won't discuss it in the class, but direct is basically just decoding as you would normally with the, you condition the output on the prefix. The channel method does what's called a noisy channel model. So instead, it is modeling the probability in a slightly different way. It is not relevant to the what we're discussing in class. You can check out the paper for the details. Okay, so this is, oh yeah.
I wonder how they measure the accuracy, because it's like random English words are having like not bad performance.
Yeah, so random English words, it looks like it preserves the format and the input distribution. So here, the labels are actually the ones that are manipulated. So yeah, I guess from a model's perspective, it sees no relationship between the input and the label. It's really unclear what it should do, right, with given a held out example. I could see how this is better than, for instance, this version where it has no format to predict, like it doesn't know that it shouldn't just continue this sentence, right? So I don't know. I think you're right that it's very surprising, especially in like this bar or here, that it's so good. But yeah, it's definitely not intuitive. Yeah.
You must have to give it some instruction, right, for it to be able to.
So these don't have any instructions. They're just.
It would still generate the correct labels in those bars.
Mm-hmm.
Just by chance.
Yeah, here, and this is not just a single task. It's averaged over many tasks. So
it predicted the task itself as
Well, the demonstrations are task specific, but I was just saying that these bars here are not from a single task, but they're the average performance over many different classification tasks.
But I guess what I'm saying is that in the previous slide, like
Yeah.
for the examples, it is supposed to be for sentiment analysis, but you don't tell it positive or negative at all in the random English word.
Yeah, yeah.
But
It still predicts positive and negative.
So I have to
Yeah.
predict that
Yeah,
those are the labels that the users expect.
that's right. So
It's like,
it's unclear.
so if your task is not sentiment analysis anymore,
Uh,
you
it-
use the random words, it would still
So remember that it still gets the input distribution though. So it will recognize that in this task, all of these sentences have some sentiment. And it recognizes the format, but yeah, it's not clear why it happens. But I will say that, back to your question, there are limitations with this study, and one is they only study these kind of simple classification type tasks. The effect of these aspects on of the demonstrations on more complex generation tasks is still unclear. And to your point, there's been many follow-up works that show different conclusions than what this paper found. So in this paper, Yu et al., they kind of rebut the conclusions of the first paper. They show that the input label mappings do matter in certain tasks and experimental conditions, and when using certain eval metrics as well. This paper I did want to look at in more detail. It is exploring the same type of phenomenon, but with chain of thought prompting, where you have to produce this rationale to explain a particular decision. Wow. I will just not respond to that and move on. You can check this paper out. It's linked in the slides. I just wanted to show some examples of this. Essentially, this shows that if you prompt the model with wrong rationales that make no sense and like they don't lead to the correct answer, you can significantly mess up the model when it's doing these kinds of math word problems. I just wanted to find one of the, so let's look at this example here. In general, something like chain of thought prompting, you would have, up here, Sean has 5 toys for Christmas. He got 2 toys each from his mom and dad. How many toys does he have now? And then the rationale you would give was Sean started with 5 toys. If you got 2 toys each from his mom and dad, that is 4 more toys. 5 plus 4 equals 9. So this is the kind of prompt that people give when they want to elicit this kind of chain of thought reasoning. So this paper looks at what happens if you give the demonstration in the prompt with some weird modifications. Like what if instead you say, Sean started with alpha toys and he got beta toys for it. So this no one would say this, right? Like pi. Or here, Sean started with 5.5 toys, which, doesn't make sense. There's more interesting perturbations. So Sean started with 5 toys. If you got 2 toys each from his mom and dad, then that is 4 more toys. And then what if the rationale is just this equation with no reference to the actual entities in the problem? Here you can see that the solve rate goes down by half if you do this from 20% to 10%. Even though this is the correct reasoning, it's just not descriptive enough, right? Let's see if they had some other nice ones. Oh, this looks like a perturbation of the text. So here, with 5 toys, Sean started 2 toys each from his mom and dad. If he got, then that is 4 more toys. I don't know why the solve rate is higher for this than. Anyway, so you can check this paper out for more examples of messed up rationales and what the impact those have on the solve rate is. Okay. So the last thing that I want to talk about is how does the large language model make use of whatever aspect of the demonstration it actually uses, right? So we've talked about all these different properties of the demonstrations, but like we don't understand how it uses these things to make its prediction. And we still don't understand that. There's just a bunch of theories which I will provide a quick overview of. And specifically on one of the readings for today, this Akurik et al. Paper, they say, we investigate the hypothesis that transformer-based in-context learners, so like large language models like GPT-4, the hypothesis that they implement standard learning algorithms implicitly by encoding smaller models in their activations and updating these models, these implicit models, as new examples appear in the context. So this is a pretty interesting experiment that they do. Actually, they theoretically prove that a transformer model can actually learn a smaller linear model within its parameters. So just as a refresher for those of you who have taken machine learning, right, this is the standard loss that is associated with a linear regression problem. And if you've taken machine learning, you know that this can be solved with a closed form solution. It can also be solved by gradient descent. So there's multiple ways to approach this problem. Basically, you're trying to find this set of parameters that minimizes the loss, this regression loss, the square loss that we talked about, right? So they set up a bunch of experiments, and also they they figure out these primitive operations that can be very useful when implementing these learning algorithms, and they show that transformers can actually do these operations through the self-attention and feed-forward layers that they have. So some functions here, this is from their paper, that could be useful is moving entries from one column to another, multiplying different blocks of matrices together, doing affine transformation. So this is pretty cool. Affine transformation, just like the WX plus B, they show that a transformer can do this operation by just setting up the attention properly and setting up the parameters. So their proof here, or what they show, is that each of these 4 operations can be implemented by a single transformer decoder layer. So there exist these query, key, value, feed-forward matrices such that given some matrix as input, you can do any of these operations. And so then you can see in their paper, they actually have these kind of insane steps where they show that this is how you implement gradient descent with a single example in the demonstration using these primitive operations that transformers can do. So obviously these are not readable, but you can just take their word for it and assume that this is equivalent to one simple step of gradient descent that we can all implement quite easily. You can see what this actually maps to, this complex object here, where this last term represents the updated parameters from doing one step of gradient descent. So this is just a theoretical result, right? It shows that it is possible theoretically for a transformer to do one step of gradient descent. Or even they show it's possible to derive the closed form solution. A transformer can do that too. So this is very interesting if this is actually what a large language model is doing, right? If you give it a new task, it's not just figuring out, oh, what is the closest example of this task that I have in my training data? It's actually saying, okay, let me use these tools that I have for training smaller models within my own parameters, and let me learn to solve this task. So essentially the model, like a large language model, has learned how to learn a new task rather than copying from its training data. So again, it's not clear if this is actually happening in large language models. These experiments were all done on smaller synthetic transformers that were trained only on these simple regression problems. It's obviously much harder to evaluate these things with access to GPT-4 where you can't look at its parameters. Yeah.
And I don't know your sufficient
How do you mean?
Like, I guess like put in a robot, like, turn on the lights,
Uh-huh.
it has a camera and you can see it moving from it. Like, it knows what the light switch is, because it both has, generation capability, taking text, taking light switch.
Mm-hmm.
So,
Yeah, I mean, it would be cool if you could do some experiment like this to figure out the model is actually implementing some more complex learning algorithm to figure out how to turn on the light switch, right? We don't have, I mean, people in robotics have built these robots already, but I don't think they've yet hooked up a large language model to this, which seems to be much more powerful at planning and reasoning than any of the existing like domain-specific approaches. Yeah.
So they presented this theory in the paper. Like you said, they did some experiments.
Oh, yeah.
Like that.
Yeah, so let's get to the experiments. I didn't cover all the experiments. So first of all, they show, like I just showed you, that transformer can implement one step of gradient descent, which is very cool because we know gradient descent is like this general learning rule. We can use it to solve or train many different kinds of smaller models for different tasks. Yeah, the last part I wanted to highlight from this paper was like, where is the evidence that this is actually happening, right? It's happening in theory. It can happen in theory, but does it happen in practice? And so this actually nicely connects to the probe network lecture that we just did last week. They train several probe networks to look for the intermediate values of computations that you would need to make if you were doing, for example, gradient descent, or if you were doing the closed form solution. So you can see here, they want to know if the model at any layer is encoding this particular quantity, which is useful for both of the, you have to compute it for both of the algorithms that they're interested in probing for. So they essentially train this probe network to, given the representation at every layer, and so the token level representations, you can probe each one of those to see like which particular representation, if any, contains this this intermediate value. And they do find that it occurs in different layers. They actually find, I think, that these intermediate computations are not present at early layers, but they are found in later layers of the model, which suggests that the smaller model is actually like distributed over many layers, and at some point you can show that the model itself has actually computed a value that is critical for doing this kind of update. So again, these are all on like quite synthetic data sets and models, but the fact that that is possible alone is quite shocking. And there have been many results like this around the same time this paper was published. So if you're interested in reading more, I would check out all the papers that cite this one. Again, this was published in this year's iClear conference, which is happening right now. So it's all very recent work, but it is, offers an alternate explanation to the one that I gave last year in this class, where I was just like, oh, they're, just regurgitating their training data. Like maybe there's something else that's going on that's much more interesting than that. Yeah. Yeah, the whole, they're not looking at actual text models. They're just looking at models that have been trained on various different functions mappings between numbers. Yeah, so that's why it's hard to generalize from this to what is actually happening in GPT-4, but it is also very cool to have like a more mechanistic explanation of the actual algorithms that the model itself might be using to solve these tasks. All right, other questions? Okay, so yeah, that's it for today. We'll have Marjana lecturing on Wednesday about machine translation, and your quiz will be available for that lecture within the next day or two. And also expect your exam grades within the next day or two as well.
Thank you.
Yep.
I have